Okay, hello everyone. So today we're going to be talking about 4.3 and 4.6. 4.3 is about binomial distribution. 4.6 is about the Poisson distribution. Both of these turn out very handy when it comes to sampling, and we'll see why that is. Okay, let's get started. Key concept and agenda. Introduce binomial random variables and probability distributions. Remember, random variables and probability distributions are one and the same thing. They describe basically the same thing. Go over 3 methods for finding it: a formula, technology, and a table. I've actually taken out the table part. Our book doesn't have a table in it, so we won't worry about that. We'll just use the formula and technology. Mainly, technology. Okay, we'll talk about parameters, mu and sigma for this thing, and then we will talk about the all-important significance idea, which will come up in hypothesis testing. Okay, that's the goal, hypothesis testing. We're all going to become experts in hypothesis testing. All right, so a binomial probability distribution results from a procedure that meets these 4 requirements. First, the procedure has a fixed number of trials, okay? So you've got a procedure that you repeat a fixed number of times. The trials must be blank, independent. They must be independent from each other. Okay, let's go on to the next 2. Each trial must have all outcomes classified into exactly 2 categories called success or failure, and that's just what they're commonly referred to as. Success isn't necessarily a good thing or not, it's just the thing you're interested in. So that's the success. This is referred to as a Bernoulli trial. A Bernoulli trial is a experiment where there's only 2 outcomes. The probability of a success remains the same in all trials. So the probability doesn't change. They're repeated, independent, binomial or binary or Bernoulli trials. Okay, notation for binomial probability distribution. So S and F, those are that's success and failure. So right, so success and failure. So X equals S or F. Now I know what you're thinking. You're thinking, well, this isn't a binomial. This isn't a Okay, so S and F, that's not exactly the random variable though. The random variable is the number of S's. So X equals the number of S's, all right? Each Bernoulli trial has the outcome of either success or failure, and we count those, and that gives us our binomial random variable, the number of successes and failures within a fixed number of trials. Okay, probability of S is equal to P. Remember, we said that would not change. That was part 4. The probability remains the same. And the probability of failure, since there's only 2 possibilities from part 3. Oh dear. Oh, where'd it go? Okay, there it is. Since there's only 2 possibilities from part 3, we have that the probability is going to be Q. And then N is the total number of trials. Okay, X, a specific number of successes in N trials. P is the probability. Let's see now, was there anything to fill in here? Yeah, there was. There's a probability of success. There's a probability of a failure. And this one here, probability of success in X, in probability of success in one of the N trials. This and P, see, so P is the probability of success in just one Bernoulli trial. And Q is the probability of failure in one Bernoulli trial. So one of those either-or trials, one of those success or failure trials. The probability of X is the probability of getting exactly X successes among the N trials. All right, so here's some notation. If X is a random variable that has a binomial distribution, B stands for the binomial distribution, then we say X tilde, or is distributed as a binomial, and there's two parameters, P and N. So P is the total number of trials, and P is the probability of success in one trial. All right, great. Okay. The word success is used here. As used here is really arbitrary and does not necessarily represent something good. Either of the two possible categories may be called the success, S, as long as its probability is identified as P. So remember, when using a binomial distribution, always be sure that the X, number of successes, P, probability of success, are linked, matched, are consistent. So if X is the number of successes, the number of times something occurs, P needs to be the number of times P needs to be the probability of that thing occurring. You're counting the things that have probability P, and that's your X. So they need to be consistent. They need to match. Okay, now we talked about the cumbersome calculation guideline when things are strictly speaking dependent, but they could be considered independent, and we're going to use that when sampling without replacement. When sampling without replacement and the sample size is no more than 5% of the size of the population, so that means that if you multiply the sample size by 20, right, 1 in 20 is 5% of 20, and so if the sample size times 5 is bigger than your population, then you can't use this. But if it's not, if your sample times 20 is smaller than your population is, then treat the selections as being independent. Wonderful. So that means we can apply the binomial distribution to sampling without replacing them, so long as the population is big enough. Okay, now here's a formula now. So methods for finding binomial probability. So here's the thing. You've got N different trials. N. And the probability of success for each one is P. Now we want to know what is the probability that among these N independent Bernoulli trials with probability of success P, what's the probability of getting exactly X successes? Well, that means that you have that means, okay, so if I wanted to get X successes, let's say the first one was a success. Well, that happens with probability P. The second one is a success with probability P. And then the nth one would need to be a success with probability P. The rest need to all be failures. So that's Q. Probability of the next one is Q all the way up to N. So I end up needing X successes times Q failures, which is N minus X failures. Now this is just one of the ways that it occurs. This was if all of my successes happened first, right? This is just one of the ways it can occur. Oh, excuse me. That would be if all of my successes happened first. But that is not necessary. And so these should be rearranged. You know, if there was a rearrangement of that sort of thing, that would also be included. And so we're going to put this term up here, which counts the number of possible ways this could be rearranged. So this is the number of times, number of ways one gets X successes. Great. Okay, so that right there is the probability distribution. See, so imagine I've got this table here that's like 0 successes, 1 successes, 2 successes, all the way down to N successes, and then N plus 1 successes. No, that's not possible. You can't have N plus 1 successes among N trials. So it's 0, and everything after that is going to be 0. But before then, it's going to be P times P of N, where I use this formula here, and I plug in my N for X. This here is going to be P of 2. It gives me that probability. I can plug it into my calculator and get something out. And yeah, I could plug in 0 here. The probability of getting 0 successes, all failures. So this defines my probability function. All right, and we already discussed about what N, X, P, and Q are. Method for finding binomial probabilities. All right, so we did that example, and now we're talking about how to find it. Method 2, using technology. So the first method we used was to use this formula here, which can be computed with some difficulty, but it can be computed. Now we're going to talk about using technology. Technologies can be used to find binomial probabilities. The screen displays on the next slide. There is not going to be any screen displays on the next slide. I'm going to show you what it is in Excel. List binomial probabilities for P equals, okay, so N equals 5, P equals that, as in the previous example. Notice that in each display, the probability distribution is given as a table. Okay, well, you don't need to notice that. Just observe what I do in Excel. So I'm going to go ahead and open up Excel. I've got this this old example. Let's see, let me get my keyboard out. Okay, so there's an example from before. I'm going to go ahead and get a new sheet here. All right, now, so I want to use the technology to find P of 3 as before. And so what I'm going to do, I'm going to hit equals, and then I'm going to, well, binomial, BI. Okay, so there's binary to decimal. Binom looks pretty good. Binom dis looks great. Binom.dis, let's do that. Binom.dis. Number S, what could that possibly mean? Number of successes. Oh, well, that's 3. Okay, comma, trials, probably means number of trials. 5 trials total, comma, probability S, probability S, probability of success. 0.85. Cumulative. What does that mean? Cumulative. I don't want to accumulate anything. I'm just going to put 0 on that one. Just enter. It's exactly what I had before. 0.138. So it worked. Let's just take a look at that again. Binom.dist, and then it basically told me what to put in. The number of successes times the total number times the number of successes, then the total number, and then the probability, and then 0 for cumulative. What cumulative does, excuse me. What cumulative does is cumulative. I see. Isn't there a way I can write on this? No. Where's the draw? Oh, nice. Okay. Oh boy. Cumulative gives. Okay, well, I don't need to draw on that. I'm going to go back to Notability. So, I could use this to fill out a probability table. So, no more draw. Go to home. Okay, so here's my table. I've got X here, and I've got P of X. P of X here. Let me do little case x because this is not the random variable, it's the values that it attains. So there's little x, and then here's this thing, and that's x. All right, it made it positive. I mean, it made it big. I am powerless to not make it big. I'm just going to go like that. There. Okay, good. So, possible number of successes are 0. Whoops. 0. Enter. 1, 2, 3, 4, and 5. Okay. Then the probability is going to equal binom, B-I-N, there it is, binom disp. For number of successes, I'm going to put that right there in. For number of trials, I'll go ahead and put in 5, 0.85, and then cumulative, I want it to be 0. Okay, enter. That's a very small number. Yeah, if it's an 85% chance that you'll find it somebody who knows about Twitter to have none of them out of the 5, that would be a very small likelihood. So let's go ahead and copy, select it all, and then paste, and then there it is. And it changed notice how it changed my cell reference there. All right, so here it is. So here's the probability distribution table. Now I want to show you what the cumulative is. So what the cumulative gives you is the cumulative probability starting from 0, from x equals 0 and going up. So watch, I'm going to go equals this thing, enter. And the next one's going to be equals what I had before plus what I have now, enter. Okay, let's go ahead and copy. Let's select all of that, and let's paste. And there it is. And notice I end up with 1 because that adds up everything before it. Okay, now watch this. Equals binom.dist. Okay, number of successes, that one again. Number of trials, 5, probability 0.085. Cumulative, what if I put in 1 now, 1 for true, as in yes, cumulative. And I push an enter, Okay, I get the same thing because there was nothing before it. But now, if I copy and drag, paste, it matches exactly what I did. Cumulative sums up the options before it. Okay, let's summarize that. So, Excel. Binom.dist x p x n p 0 false, don't want cumulative, gives me p of x, the probability of just x. Binom.dist of x n p 1 true equals the probability of not only getting x, but the probability that big X is less than or equal to little x. This one here is a shorthand. Probability of little x. Okay, and this also you'll see equals the sum from I equals 0 all the way up to little x of p of I. It's the sum of all the ones that came before it. That's what the cumulative gives you. Sometimes you'll want cumulative and sometimes you won't. Okay, this is very important. All right. Okay, the overtime rule. Okay, now this is super interesting. Hey, moving on. Using mean and standard deviation for critical thinking. Okay, so for binomial distributions, the mean is going to be what? Well, how many times would you expect something with probability p to happen if I repeat it n times? N times p. That's the mean. As it turns out, that's what the mean is. The variance, it turns out, if I were to use that table, that table that I made in Excel, if I were to use that table to compute the variance, I would end up getting this. This is a good bit of mathematics here. They really simplified that down. That's NPQ. It's very simple. The square root, the standard deviation, is just going to be the square root of NP times Q. Okay, so that's what the parameters are. I'll just give those to you. All right. And so with the range rule of thumb, significant values, so remember the range rule of thumb, values are significant if significantly low if they're more than 2 standard deviations below the mean, and they're significantly high if they're more than 2 standard deviations above the mean. And they're not significant is if they are within that interval. Using probabilities to determine when results are significantly high or low. Okay, here it is again. I'm just going to harp on this because it is so germane to hypothesis testing, which is my goal, to have everybody be experts in hypothesis testing. Okay, significantly high number of successes. X successes among n trials is significantly high if the probability of X or more, we're trying to establish that it's high. So if the probability that X or more is 0.5 or less, if it's that or even smaller, then it's going to be significantly high. That is, X is significantly high, is a significantly high number of success if P of of x or more successes is less than 0.5. Significantly low is similar. X is a significantly low number of successes, meaning there's something funny going on. It's not just by chance, right? It's perhaps our null hypothesis, perhaps our assumption is wrong because something funny happens. Something's is happening. Why am I getting a significantly low number of successes? So x successes among n trials is significantly low if the probability of x or fewer successes is 0.5 or less. Still or less. It's a small probability. That is, x is significantly low, is a significantly low number of successes if that or fewer, if that probability is less than 0.05. Okay, and so here's the rationale, which we sort of already went outcome. The number of outcomes with exactly S successes among n trials. You get that many of them. And then this is the probability of X successes among n trials for any one particular event. So there's the X successes, there's the rest of them as failures. Great, so there's that example. All right, geometric distribution. Okay, we're not talking about geometric distribution. This is 4.6. Poisson distribution. Okay. All right, key concept and agenda. So what we're going to do, we're going to talk about the Poisson probability distribution, which is another category of discrete probability distributions. We'll define the Poisson probability distribution. We'll discuss its requirements, its parameters, and its properties. Then we're going to look at an example, and then we're going to use it to we'll discuss how it can be used to approximate the binomial distribution, and then we'll go to another example. Poisson probability distribution. So a Poisson probability distribution is a discrete probability distribution that applies to occurrences of some event over a specified interval. Now that interval can be pretty broad. Like, think about anyway, we're going to go into more examples, but that's pretty broad. Anyways, this is a pretty useful thing. The random variable x is the number of occurrences. Now, this would be great. I'm glad all of us are writing this down because it's really important. Number of occurrences of the event in an interval. So there's a specified event, there's a specified interval. X is the number of occurrences in those intervals. The interval can be distance, area, volume, or some similar unit. Some examples are dents on a car. The car is the interval in this case, and the number of dents is the thing that happens. Is assuming that the dents are just sort of random and uniformly distributed, which in actuality they're not. Another example could be customers during a certain hour or so, or something. Number of customers in a store. How many customers do we get? Okay. Poisson probability distribution. The probability of the event occurring x times over an interval is given by... Now, this is very difficult to see or to explain. But basically what it is you're going to be given mu as a parameter, and you raise mu to the x, then you multiply that by e to the minus u, mu. Then you divide by x factorial. You could compute that. You could throw all those numbers in your calculator and be just fine and get your answer. So e in this case is a very special number. Yeah, what is e? E is a very special number that's significant in calculus and finance. And it is called, and anyway, it's a value like pi. And the value is 2.7182818282459. Anyway, you don't need to write all that. 2.718 is fine. Okay. Mu, mean number of occurrences of the event in the interval. That's what mu is going. So that's what mu. So first you have a mean number of occurrences event in this in the interval, and this is usually given or usually obtained empirically, meaning you found it from data. Okay. Notation for the Poisson distribution. So there's the Poisson probability distribution P, and it's just going to be, we're going to say X is Poisson distributed with parameter mu. The only parameter is mu, which is usually given. We don't need to come up with it, it's given. Or we may need to compute an average. May need to compute an average. Okay, requirements for the distribution. So the random variable x is the number of occurrences of an event in some interval. The occurrences must be independent, meaning they one does not depend on the other. The occurrences must be. Oh, hold on. Let's see. I put this thing, okay. Let me select this, move it down here. That should be independent. This one here, they need to be random. Random. The occurrences must be random. The occurrences must be independent of each other. And then for 4, the occurrences must be uniformly distributed. So it wouldn't necessarily be a good thing to use this for number of customers throughout the day because customers do not come in with uniform distribution, with just at a rate that's constant throughout the day, or even roughly constant. There's much fewer customers that come in just after opening and just before closing in a lot of businesses. Or perhaps certain businesses have it the other way around, where they've got a lot of people coming in at the beginning and then it slows down after that until it picks up just before the end, like maybe the DMV or something might experience business more like that. Either way, it's not uniform. However, if you did it just maybe within a particular hour or a particular block of 30 minutes, that might be, you could definitely argue uniformity more easily for something like that. Okay, Poisson probability distribution parameters and properties. So the only parameter is the mean, which is mu. The standard deviation of sigma is the square root of mu. Now, isn't that interesting? This isn't always the case. It's only for this probability. So this right here is only for Poisson. That's one of the neat things about Poisson, is the standard deviation is just the square root of the average. Isn't that interesting? Properties of the Poisson probability distribution. A particular Poisson distribution is determined only by its mean mu. A Poisson distribution has possible values of x, and it just goes all the way to infinity with no upper limit. Okay. It's still discrete, even though it's infinite. It's still discrete because it fails the in-between test. There is no number of occurrences in between 1 and 2, so this is not continuous. It's not a continuous random variable. It is a discrete random variable. Okay, here's an example now. And this is a very important example. This is not a blue example, okay? I want to see us doing this on all these slides. Example, Atlantic hurricanes. For the 55-year period since 1960, there were 336 Atlantic hurricanes. Assume the Poisson distribution. So there's lots of times when you should not. Okay, there's a number of reasons why the Poisson distribution is not, strictly speaking, a good model for the occurrences of hurricanes. However, we're going to make assumptions and do it anyway, and we'll see how well it does for us. Okay, find mu, the mean number of hurricanes per year. All right. There were 336 total, and there was 55 years. So there it is. So 336 divided by 55 gives me 6.109. 09. Let me just go like that. That's my mu. That's the average number of hurricanes in a year. Find the probability that in a randomly selected year, so some random year, there were exactly, so the year is the interval. The year is the interval. The number of hurricanes is the number, and a hurricane occurring is the event. So we're going to use the Poisson probability distribution to count the number of times a hurricane occurred within that interval, 1 year. Okay, find P of 8, right? That's exactly the eight hurricanes, where P is the probability of X Atlantic hurricanes in a year. Okay, what do I do? Okay, and then there's another one, but we can do this one right now. So, hurricanes. Okay, so we're not going to go through the requirements very much because we know that they might fail. This might fail to approach all of those, to meet all those requirements, but we're going to assume that it's that you can use a Poisson distribution. But basically it does meet all the requirements in that we're assuming that so hurricanes don't necessarily appear uniformly throughout the year. All right, so that's a problem. We're assuming that they do, though, and that assumption is not very valid. But is it good enough to get something by, to get some useful information? Hurricanes are not necessarily independent, in that I don't think you could have two hurricanes nearby each other at the same time, and so there's some sort of they're not, strictly speaking, independent. But we're going to assume that they are and see how far it gets us. So let's go ahead and assume this is a probability, a Poisson distribution. Okay, so let's go to the Excel. So P of 8, let me just memorize some of these numbers here. 6.01. All right, let's go. So I'm going to go here to Excel. Get out my keyboard. All right. So P of, so this is the Poisson distribution now. So I want P of 8 here. And that is going to equal, what? P, that's going to equal, well, P-O, oh, there it is, Poisson distribution. X is 8. Mean is 6 point, no, you know what? Let me put in the exact number. 336 divided by 55. That'll give me the best possible value there. And then cumulative, I don't want 8 or less, I just want 8. So I'm going to put 0 there, enter, and there's my probability. 0.0, let's see, 0.10697. I'm going to round that to 0.107. So P of 8 is 0.107. All right, great. Found that. Okay, for the 55, all right, so in this 55-year period, there were actually 5 years with 8 Atlantic hurricanes. How does this actual result compare to the probability found in Part B? Does the Poisson distribution appear to be a good model in this case? All right, so there were actually 8 out of 55 years that had, no, sorry, there were 5. There were 5 in the 55 years that had 8 hurricanes. And so the probability of 8 can be approximated by 5.8 empirically, because we count the number of times it occurred. There was 8. How many times were there 8? There were 5 out of 55. Now, that probability is 5 out of 8 is 0.0909. And what we found using Poisson is 0.107. And so the difference there is, well, the difference there is quite small. Less than 1%, I think, difference. So these are really quite close. No, maybe 10%. Well, let's just see. 0.0909 minus 0.107. Okay, so the absolute difference is 0.0161, and the relative difference is 0.17, so about 17% off. Among small numbers, that's not so bad. So there it is. So was it a good model? Surprisingly so. Another thing is that our probability suggests that there would be 0.107 times 55 is 5.885. So our model would predict that in a 55-year period, there were 5.885 years that 8 hurricanes occurred. And that's pretty close to 5. So there's some stochastic modeling there. All right. Okay. Poisson distribution as approximation to binomial. The Poisson distribution is sometimes used to approximate the binomial distribution. When n is large and p is small. One rule of thumb is to use such an approximation rule of thumb is to use such an approximation when the following two requirements are both satisfied. When the number of trials is greater than 100, and when the average times that something occurs is less than 10. All right. If both requirements are satisfied, we want to use the Poisson distribution as an approximation for the binomial distribution. We need a value for mu, though. Well, we'll just use the mu from the binomial approximation, which is n times p. So that's how you do that. All right.